Hi everyone. In today's video, we're going to be talking about the regiochemical outcomes of Diels-Alder reactions, and then we're going to take a step back to think about Diels-Alder reactions and all cycloadditions and describe them using molecular orbital theory. So it's my hope that by the end of this video, you would start to understand what affects the regioselectivity of Diels-Alder reactions when there is one, and you can start to predict what those outcomes will look like. Then you will be able to describe cycloaddition reactions writ large using molecular orbitals. And lastly, you'll be able to determine whether a reaction considered a cycloaddition reaction is symmetry allowed or symmetry forbidden under thermal or photochemical conditions. And so we will begin our discussion with regiochemical outcomes. And there are really two scenarios you're going to want to focus on. In the first scenario, we want to focus on reactions where either the diene or the dienophile is symmetrical. In this scenario, we actually don't have to worry about regioselectivity because a molecule with only one constitution is formed, or one constitutional isomer is formed in this scenario. So here's a Diels-Alder reaction with a symmetrical diene. So we've actually seen this before in previous videos, and by now, hopefully you're able to understand and predict the product of this reaction, actually. We should expect two isomers of your product to be formed, but they both have the same constitution. So that's fine, and that's because you have a symmetrical diene. In this second example, we have a symmetrical dienophile. Our diene is no more symmetrical, but it doesn't actually matter. We're going to form two molecules, also stereoisomers, that are the same constitution. And here are the two molecules that you would form. Okay, so we see here that we form the two stereoisomers where your two dienophile substituents are still cis, substituted on the ring, but there are now two possible stereoisomers in which you could have cis disubstituted dienophile substituents on the ring. Same constitution, so these are not, there's no regioselectivity that matters in this particular reaction. However, the situation does get more complicated if you have both an asymmetric diene and an asymmetric dienophile in your flask. So here's an example of an asymmetric diene, and here's an example of an asymmetric dienophile. In this scenario, now you do get regioselectivity. Here, there are two possible constitutional isomers in your Diels-Alder product that you can get. You see here where you have the aldehyde 4 carbons away from the ether oxygen as your major constitutional isomer in this reaction, versus the case where your aldehyde, which is in green, is 3 carbons away from your ether oxygen, which is in blue, and that is your minor constitutional isomer. Please note once again, this is from our previous video, that while you are seeing regioselectivity, both stereoisomers of your major constitutional isomer will still be formed. So you still want to make sure you put the wedge and the dash on that aldehyde carbon. And so that just makes sure that the stereochemistry is still invoked there. But we're focusing on regiochemistry today, so I'm just going to show you, we're going to explain why we get regioselectivity in this reaction. And the key way to understand why there's regioselectivity is by analyzing the electronics of both the diene and the dienophile. So let's start with the diene, and then we'll go to the dienophile. So with the diene, we realize that that ether oxygen is 1 carbon or adjacent to a pi bond, which means we should expect that a resonance form can be shown and will happen such that the lone pair delocalizes into that pi system. And so once you draw out your resonance hybrid, we will then be able to see that there is a buildup of electron density on one end of our diene, right? So there's only one end that has a partial negative charge, and that is the side that is adjacent to that ether oxygen. So take note of that particular position on our diene, and let's compare that with our dienophile. With our Dienophile, we also see that we can essentially engage in resonance forms here. Remember, this is a polar pi bond, which places a positive charge on the carbonyl carbon, and another resonance form can be drawn, which then places a positive charge on one end of the dienophile. Remember, the dienophile is just the two atoms in the pi bond that is going to be engaging in the Diels-Alder reaction. And so if we draw out our resonance hybrid, we see that one end of our dienophile is actually deficient in electron density. Okay, so we're focusing on this hybrid because that helps us understand the more realistic electronics of our diene and our dienophile. Okay, so with these two hybrid structures of our diene and dienophile in mind, the most likely way these two molecules are going to try to lock up is to ensure that the most negative side of the diene is linking up or forming a bond with the most positive side of the dienophile, right? So just thinking about how the charges are going to want to like interact with each other. Okay, and so what we're going to do is draw out a transition state that will achieve this goal, where the most negative end of the diene is interacting and linking up with the most positive end of our dienophile. And if you do that properly, you will start to see how we get to the major constitutional isomer of this reaction. So the two starred locations is where I have the most negative end of our diene interacting with the most positive end of our dienophile. But doing so would mean that like you'd have to sort of essentially flip the dienophile in this scenario such that they line up. And that's how we get to our major constitutional isomer. And once again, please note that all stereoisomers in this scenario are still formed. So you will still want to draw the aldehyde in a wedged and in a dashed position as well. Okay, so that's really it for the regiochemical outcome. You want to really analyze the electronics, and then you want to line up the most negative end of the diene with the most positive end of the dienophile. Okay, so next we are going to then turn the table line, now in many ways, take a step back to really think about these cycloaddition reactions and using some fundamental molecular orbital theory to understand this reaction. And you would see that it actually becomes important when you want to figure out what conditions is going to allow for a cycloaddition to work. And there are two conditions we're going to focus on. The first being Diels-Alder cycloaddition reactions that are performed under thermal conditions. And we will use our standard Diels-Alder reaction to really elaborate on what we mean by describing this reaction or cycloadditions under thermal conditions. Under thermal conditions, we simply mean that our diene and dienophile are reacting with heat. And that heat is denoted by that delta sign on top of the arrow. So this is a heat-based reaction. And under these conditions, both of the reactants, so both the diene and the dienophile, are both molecules involved in the cycloadditions, are in their relaxed electronic state. And so to truly understand what that means, we have to focus on the pi molecular orbital system of both of our molecules. Okay, so going back to some fundamentals, we know that in our diene, we have four atoms involved in the conjugated pi system. And within that conjugated pi system, there are four pi electrons. So if you look at your diene, we see that there are two double bonds essentially. I remember that each pi bond on there contains two electrons. So that means there must be four pi electrons total in this pi system. So to draw out our molecular orbital picture for the pi system of a diene, we start off in our level one, where all four p orbitals involved in the pi electron system are in the same phase. And so that means they're just completely constructively overlapping across each other. And that's our first wave function. And as we move up, just as a recall, we start to introduce nodes, which means a destructive interference in our molecular orbital picture. And we always start in a symmetrical way from the middle, and we make our way out to the end of our pi molecular orbitals, which means that our second energy level for our pi molecular orbital should look like this, where a node is now placed right in the middle of the pi molecular orbital. We denote that by switching the phase between p orbital 2 and p orbital 3. And then our third molecular orbital level should look like this, where now there are two nodes. See the symmetry, they sort of like are spreading out. So now the two nodes, one is between p orbital 1 and 2, and another node between p orbital 3 and 4. Note that whenever you have a node, you switch the location of the phase of the wave. And then our last and highest energy molecular orbital should look like this, where now you have a node essentially in between each of the p orbitals. And so now you have three nodes. So you see how we increase the number of nodes as we go higher and higher in our energy levels. And so there are four of them. There are four pi molecular orbitals for our conjugated diene with four p atomic orbitals. And now we fill up the four pi electrons using the same principles we've learned in general chemistry and earlier on in this class on the off-bound principle, the Pauli exclusion principle, and what have you. So we start off by filling up from psi 1, we pair, and then we go up to psi 2. And if there are four pi electrons, it would mean we should end our electron filling up at psi 2. Okay, so that's for our diene. Now let's look at our dienophile. In our dienophile, we are only dealing with two p atomic orbitals because we're just dealing with one pi bond in our Diels-Alder reaction. So we only worry about the molecular orbital that is consistent of two p atomic orbitals, which would mean that there should only be two pi molecular orbitals to worry about. The first one being the scenario where both of those molecular orbitals are in phase, and so you should have no nodes. And then the scenario where both of those orbitals are out of phase, and so now you have introduced a node in between those two p orbitals. And that's it. You should only have two pi molecular orbitals for a system with two p atomic orbitals. And now, if you want to fill up the pi molecular orbitals with the two pi electrons, we should end up at psi 1. So the two electrons should end up pairing in psi 1. Okay, so now in our typical Diels-Alder reaction, we think about it as an overlap of the highest occupied molecular orbital of the diene, so the place where you have a lot of electron density, which is typically your HOMO, or your highest occupied molecular orbital. And then you overlap that orbital with the lowest unoccupied molecular orbital of the dienophile. So that's the place where there's a lot of electron deficiency. There's no electrons in there. And so you can imagine a favorable overlap is one where you have an electron-rich diene orbital. so the HOMO, with an electron-poor Dienophile orbital, which is your LUMO. So in the relaxed state, so your thermal condition, so you don't have any excitation, everything is back down and where they should be, which is what the system looks like right now. The HOMO of the diene should be site 2. So look at the picture of site 2. And the LUMO of the Dienophile should be site 2 in the Dienophile. Okay, so what we should be looking at here is the HOMO of diene, which is site 2 in this case, and the LUMO of diene of the Dienophile, which is also site 2. Okay, so we're just going to focus now on the HOMO of the diene, which I pictured on the left, and the LUMO of the Dienophile, which I pictured on the right. And we have just described that for Diels-Alder cycloadditions, you want to make sure that you are overlapping the HOMO of the diene, or your electron-rich species, with the LUMO of the Dienophile, which is your electron-poor species. And so what we're going to look at here is what does this overlap look like on the thermal conditions? And so what I've sketched out here are the HOMO orbitals for your diene on carbons 1, 2, 3, and 4, and the LUMO orbitals of your dienophile on 1' and 2'. Remember that all we care about are the 4 atoms of the diene and the 2 atoms of the dienophile that are involved in our Diels-Alder. And please make note here that track that your HOMO orbitals are indeed sketched out properly. So we see here that in the site 2, so your HOMO of your diene, there is a node between carbons 2 and carbons 3, and therefore you get a switch in the sign of the wave. So that red shaded area is now at the bottom and no at the top, right? So that make sure that that's the case because that is going to map on as your HOMO of your diene. And likewise, in the LUMO of your dienophile, there's also a node in between 1' and 2', right? So that is indeed consistent with the LUMO of the dienophile. But note that as long as you keep that node in between those 2 atoms in the diene and dienophile, where that shading is really dependent on you. You could have switched it where the red shading on 1 and on 2 of your diene are actually below, and then 3 and 4 are above for your diene. Or you could have switched the dienophile where 1', the red shading was above, and for 2', the red shading was below. It doesn't matter as long as you keep the nodes correct in your diene, your dienophile. But what you want to do is see, can you map on the shaded area between your diene end and your dienophile end, or the unshaded area between your diene end and your dienophile end? In other words, can you make sure you have a constructive overlap between 1 and 1' and 4 and 2'? And under thermal conditions, we can see that we can. In fact, we see that between 1 and 1', if you try to overlap where the diene is essentially above the dienophile, then the unshaded area of your diene orbital at carbon 1 can actually overlap really nicely in a constructive manner with the unshaded area of your dienophile 1'. And once again, we're thinking about the diene being like on top of the dienophile and essentially closing in from above. And likewise, because there's a node between carbon 2 and carbon 3, the sign of the p orbitals in 3 and 4 flips. So while the bottom of the 1 orbital is unshaded, the bottom of the 4 orbital is shaded, which matches on perfectly with the top of 2', where it is also shaded. And so now you can have another constructive overlap between the 4 orbital and the 2' orbital. And so we see that on both ends of our cycloaddition, we see a constructive overlap when you sandwich essentially the ends of the orbitals on top of each other. And because that's the case, we say that under thermal conditions, where both of your reactants, so both the diene and the dienophile, are in their relaxed electronic state, the Diels-Alder 4 plus 2 cycloaddition is symmetry allowed. And that symmetry allowed simply means that the ends of your pi molecular orbitals, so the HOMO of your diene and the LUMO of your dienophile, they overlap constructively in the cycloaddition. So both sides have to overlap constructively for this to be symmetry allowed. Okay, so we just confirmed through molecular orbital theory that under thermal conditions, which means under heat, Diels-Alder reactions should work. We should expect to see the Diels-Alder product, and that's because the overlap of our HOMO orbital of a diene and our LUMO orbital of a dienophile under thermal conditions is symmetry allowed. So the orbitals at the end of those dienes and dienophiles overlap constructively. Now let's contrast that to the situation under photochemical conditions. Now we will use that to understand why um, knowing molecular orbitals is important to figure out what conditions are necessary for cycloadditions. So under photochemical conditions, we mean simply that the reaction is performed under light. So H nu on top of the arrow signifies that you're doing this under light. But the system hasn't changed. We are still using the diene and we're still using the dienophile, which means our molecular orbitals should look exactly the same, regardless of the conditions that we are doing this in. This means this picture that we drew earlier on should stay the same for the diene and the dienophile. So that shouldn't change. However, what is different about the photochemical conditions is that unlike in your thermal conditions, when both reactants are in their relaxed state, under photochemical conditions, one of the reactants, typically the diene, is in the excited state. And we've talked about the molecule in its excited state in the past. It means that one electron should have jumped up from the HOMO orbital into what was the LUMO orbital, so the closest unoccupied molecular orbital in energy, and that shows an excitation. So let's draw out the electronic diagram of the diene in the excited state. And here is the electronic diagram for the diene in the excited state. Note that we have essentially popped up one of those electrons that was in site 2, and we've put that in site 3. So that's the excitation. But what that means now is that there is a new HOMO, or a new highest occupied molecular orbital, which is site 3. So now site 3 is our highest occupied molecular orbital for our diene. The dienophile, on the other hand, still stays in its relaxed state, so that will still be with the case where the two electrons are in site 1. And so LUMO, our lowest unoccupied molecular orbital, is still site 2. So that hasn't changed. So we only excited the diene and not the dienophile under photochemical conditions. The molecular orbital description has also not changed in the sense that we are still trying to overlap the HOMO, or the highest occupied molecular orbital of the diene, with the lowest unoccupied molecular orbital of the dienophile. It's still the same definition. The only difference now is that the HOMO has changed the diene. It's no more site 2, it's now site 3. So now we're going to use site 3 of the diene, and we're going to try to overlap that with site 2 of the dienophile. And we're going to see if we're going to get constructive overlap between these two orbitals in our cycloaddition. And just to refresh again, once again, I have drawn now the new HOMO, which is site 3 on the left-hand side. So notice the shading. Notice there are two nodes now. And the original LUMO, we haven't changed the LUMO to dienophile. That's still site 2 of the dienophile, which is on the right. And now I'm going to once again show that picture of the overlap of the HOMO of the diene drawn on the molecule with the LUMO of the dienophile also drawn on the molecule. Okay, so once again, here is that picture that we talked about. So notice, once again, all we're looking for are the nodes. Where are the nodes of my diene and where are the nodes of my dienophile? Are they consistent with the picture of our HOMO and the LUMO respectively? As long as they are, that's all that matters. So we see the two nodes on our diene, which is consistent with the HOMO of the diene. And where you shade it, all that matters is that you flip the like shaded once you reach a node. And then here is a node of our Dienophile, and it's right in between the two p orbitals. And once again, what we're trying to do really is to try to map on the end p orbitals of our Diene with the end p orbitals of our Dienophile. And we're trying to see, do we get a perfect constructive overlap between the two? Remember, once again, our Diene is above, the Dienophile is below. And so we are sandwiching the bottom of our Diene p orbitals with the top of our Dienophile p orbitals. It's my hope that while you might see that there is a constructive overlap between one end of our Diene Dienophile p orbitals, there is a destructive overlap between the other end of our Diene Dienophile p orbitals, and that is denoted in the fact that we have a phase mismatch of our p orbital end on the Diene with the p orbital end on the Dienophile on at least one of the two sides of this particular cycloaddition. And so once you've introduced one destructive overlap in this cycloaddition molecular orbital, it would mean that under photochemical conditions, which is when one of the reactants, typically the diene, is in the excited state, Diels-Alder 4 plus 2 cycloadditions are symmetry forbidden, which means that we should not expect to actually observe a Diels-Alder product if we tried to do a Diels-Alder reaction with light as opposed to with heat. And molecular orbital theory actually helps explain why we shouldn't expect to observe the Diels-Alder product under these conditions. Okay? And so we see here a nice way of trying to understand and predict the conditions, whether thermal or photochemical, we should use to actually do a cycloaddition, right? And these theories can extend beyond 4 plus 2 cycloadditions or beyond Diels-Alder reactions. And in fact, what I want you all to sort of think through on your own or in groups before coming to class is thinking about, does this reaction, so this is now a 4 plus 4 cycloaddition, is this reaction symmetry allowed or symmetry forbidden under thermal conditions or under photochemical conditions? So can you use the molecular orbital theory that we just discussed to try to work your way through if this reaction will be allowed if you try to do it in heat versus if you try to do it in under light, right? And you can use the same concept. The only difference now is that instead of a 4 plus 2, both of your pi systems are involving 4 atoms in the p orbital. And so you want to make sure you're using the correct pi molecular orbital on the thermal and on the photochemical. Okay, so best of luck as you work through that before we get to class. Okay, so in this video, we've sort of gone over the regiochemical outcomes of Diels-Alder reactions. We really talked about two major scenarios, one involving symmetrical dienes or dienophiles, and the one involving where there are asymmetric dienes and asymmetric dienophiles. And we talked about this regiochemical outcomes, how you can predict those. And then we described cycloaddition reactions using molecular orbital theory. We focused on the 4+2 cycloaddition as an example or as a case study for this. And then we then used molecular orbital theory to help us determine whether the reaction would essentially work under light, so under photochemical conditions, or under heat, which is under thermal conditions. Okay? Thank you so much for watching this video, and I will see you in class.